In this video, we'll show an example of solving a second-order non-homogeneous equation using variation of parameters. So, for variation of parameters, we first need to find the homogeneous solution, and then we can use that to build up to the non-homogeneous solution. So in this case, we look for the homogeneous problem, which has characteristic equation r squared plus 3r minus 4 equals 0. This factors as r plus 4, r minus 1. So the solution here is y of t, c1 e to the minus 4t plus c2 e to the t. So in particular, we have y1 being e to the minus 4t and y2 being e to the t. Now, to solve the non-homogeneous part, we guess y of t is u1 of t times y1 of t plus u2 of t, y2 of t, or in this particular case, u1 of t times e to the minus 4t plus u2 of t e to the t. And we're going to solve for these functions u1 and u2, multiply them in, and see what that gives us. We could plug this and work it out by hand again, but the formula is always the same. It's always going to give us that u1 prime of t is negative g of t times y2 of t over y1 y2 prime minus y1 prime y2, the Wronskian in the bottom, and u2 prime is positive g of t times y1 over the same denominator. So we know that for this case, our g of t is 3 e to the 2t. We can also work out our Wronskian to make it easier to solve things out. The Wronskian here, y1 y2 prime minus y1 prime y2. y1 was e to the minus 4t. y2 is e to the t, its derivative is just e to the t. Minus y1 prime is a negative 4 e to the minus 4t. y2 is e to the t. So I'm going to get an e to the minus 3t plus 4 e to the minus 3t, or a 5 e to the minus 3t. So then with this, we can figure out that our u1 prime is going to be negative g of t, which is 3 e to the 2t, times our y2, which is e to the t, over 5 e to the minus 3t. The Wronskian simplifies to a negative 3/5. That's either 3t on top with a minus 3t on the bottom. That's going to be an e to the 6t. And my u2 prime is going to be g of t, 3 e to the 2t, times my y1, which is e to the minus 4t, divided by, again, 5 e to the minus 3t. So I get a 3/5. That is a e to the minus 2t on top, e to the minus 3t on the bottom is an e to the t. Now I can integrate both of these so that u1 is going to be negative 3 over 30, the 6 times 5 on the bottom, e to the 6t. I'll put a plus c1 here so we can see where that goes. And u2 is going to be 3/5 e to the t plus c2. And my solution is just u1 times y1 plus u2 times y2. So my yp of t here is going to be u1 1/10 e to the 6t plus c1 times y1, which was e to the minus 4t, plus 3/5 e to the t plus c2 times e to the t. This will be negative 1/10 e to the 2t plus a 3/5 e to the 2t, which gets me a 1/2 e to the 2t. And then what's left is a c1 e to the minus 4t plus a c2 e to the t, and that works for any c1 and c2, but that's not surprising because if I scroll to my general solution, for the homogeneous part, I get exactly this part. So any choice here doesn't affect my answer because that solves the homogeneous problem. So the important thing that I get out of the solution is this extra 1/2 e to the 2t, which is the same thing we got for the previous example, solving this by undetermined coefficients. So this here actually gives my general solution y of t because it already has the homogeneous part built into it, the c1 and c2 part. So that's how you would set up and solve an example using variation of parameters. It's a very formulaic method. It works this way every time. It just depends on being able to actually evaluate these integrals of u1 prime and u2 prime. There is a decent chance that depending on how complicated the problem is, you might not be able to evaluate those integrals, in which case the method isn't great because it's hard to work that out. Or even if it's possible to work them out, it might be really difficult. And so balancing the difficulty of the integral versus the straightforward formulaic process of the method is an important choice to make when trying to decide if you're going to solve a problem using variation of parameters or undetermined coefficients.